But like I said, this is going to be a review of 8th grade and added like a little bit more difficult math, but pretty much it's going to be the same. In the end, we're going to end up with pretty much the concepts from there. So we have energy here, which is our next toolbox that we have. So in our bag of tools, we started off initially with graphical analysis, which was great because it dealt with everything, but it was a pain because you always had to graph, derive, find slopes, and it just wasn't very fast and efficient. So what we did there is then we used equations of motion, which is derived from those, so it could speed things up. Unfortunately for that, you had to have constant acceleration. Forces was another tool that we have, but also limited to constant acceleration as well. Our last one, at least for this semester, is going to be energy. We're going to do energy and then momentum, which is collision, and that's how we're going to end out our semester for the next 3 weeks. And it's just going to be based on that. So there's another tool for this one. We're going to also ignore some outside forces, and we'll get to it. On this slide, you can see that I have a picture of a bunch of different types of energy, but I like you to list in your chat, in our chat, what kind of energies that you could think of. It could be stuff that you learned from in 8th grade. It could be other kind of energies, but any kind of energy that you could think of. Okay, good. We have nuclear energy, solar energy, kinetic, so if you're hearing my typing, I'm doing a poll for our next question. I can't save it ahead of time, and my computer crashed, so I couldn't save it anyway. So let's look at it. Let me make sure that this doesn't get deleted on me. So let's see what we got. We have hydropower, mechanical, elastic, electricity. Great. Let's see if do we have. What would the battery be other than electrical? So eventually it does make electrical, but what does it start off as? Magnetic, very good. So we have magnetic, we have potential, we have nuclear, geothermal, we have hydro, we have technical electricity here, which is these are both potentials. And then we have battery, which is I don't think anybody said it, but it is chemical. So initially starts off as a chemical reaction, forces electrons in one direction, which then becomes electrical. Here's another kind of diffusion or potential. Has a potential instead of going down, it's potential going up because it is a bunch of balloons. So those are different things, and I don't think I've seen strong forces, but those are, you can have forces within the atom itself. So nuclear is one, but we can have forces inside. Now in 8th grade, you might have seen this contraction before. It is a cool little tool to kind of go over the concepts that we want to go over today. So my question is, which one will be the quickest, which one will be the fastest, and how will we know? Okay. Another example of it is this ride that I experienced when I was younger. It is at Raging Waters. You'll notice there's 3 different tubes. I have to look up the YouTube really fast again. There's 3 different tubes that you could go down, and these different tubes will kind of result in different places that you're going to be. So notice that this one, the middle one's straight down. This one goes around, this one goes around. So it's kind of like our previous one. Which one do you think will get down the fastest? Which one do you think will be the quickest, I guess? So quickest means how fast you can get down the fastest, or I'm mixing my words. Quickest means the time-wise. Which one will get you down the least amount of time? Fastest would be what's the fastest velocity at the end. So here's a YouTube if you decide to watch, but let's answer the poll. So let me launch it. So the first poll is going to be, which slide do you think will be the quickest down, the shortest amount of time? And then the second slide would be the next question is which one will you be the fastest, highest velocity at the end? So for pole 1, we kind of have a good amount except for red. For pole 2, looks like red is the one that's going to be the biggest one. So we'll kind of come back to these at the end of our kind of lesson to see where we are. But keep on voting because not everybody voted. Do you guys get to see the results too? Oh, you guys don't see the results? Oh, here. Sorry. Show everybody the results. All right, so keep answering it. You could keep answering as you kind of go through it if you haven't. But this is stuff from 8th grade. So energies for physics. I think somebody said it. So we have, Vincent was the first one who said kinetic, and then Matthew said potential. So those are the two that you learned in 8th grade. Potential is stored. So we have gravity, spring, elastic, stuff like that. And then you have kinetic, which is just motion. So we'll kind of talk about the two there. Energy is kind of another way to measure force. So in this case, it's the ability to do work. So what is work? Okay. Remember, force causes a mass to accelerate. So work is the amount of force. It's easier to think of it over time, but that's not the correct way. This is more of a misconception. The more correct way is to think of it over distance. So it's the amount of force over a certain amount of distance that it's exerted. And the reason why time isn't a great example of it is because you could be doing something that for you, you're exerting a force and it takes energy to keep that up, but you're not doing any physics work. So example is if you ever got punished, I got punished as a kid like this. Hold something up with your hands, arms straight, and you have to hold it up for at least like 10 minutes, right? Or even if you're doing a workout for a sport. If you're doing that, you're doing no physical work. Physical as in like physics, because you're not moving the object. You're just holding it there. You're storing that energy for potential energy. The energy's there because it has potential, but you yourself are just holding it there. So even though you're consuming calories and actually struggling to keep it up, you're not doing any physics work because you're not doing any distance traveling. So there's the misconception is in real life, we do over time exert a force, but it does not equate to force or work as in terms of physics. So physics only works if there's a distance. For potential energy from 8th grade, you should have remembered that the potential to do work has to do with work times distance. For potential, it's going to be how big over your head. So example that I usually do in class, I have like a rubber ball or volleyball, hold it over my own head or somebody's head, and I'll drop it at 1 centimeter. Doesn't do anything, but if I drop it from a foot, even though it still doesn't hurt, it's going to do more damage or more work. If you do it from a meter high, you're going to feel it more. And then I kind of bring up other examples of that. So if you want to move somebody's head with a ball, a ping pong or a balloon doesn't do much because the mass is very small. But if you have, let's say, a heavier object or something with more mass, it has the more potential to do more work. Looking at the units, you have mass times gravity times height. So that's kilograms, meters, seconds, meters. If you remember from last unit, this is MA, so that's mass times A, so that's newtons right there, or force. So it's either Newton meters or joules. That's how we measure work. So it kind of related to chemistry now. So remember in chemistry, you measured energy in joules. In physics, we also measure energy in joules. So the amount of work you do is the amount of energy that you created or used up. For kinetic, it's the exact opposite of potential, is the motion itself. So here's the equation I have from 8th grade, 1/2 mv squared. For your homework, I'm going to ask you to try to derive it. If you do your best, spend like 5 minutes. If you could do it, keep on going and spend maybe 10 minutes. But if you're just stuck, just stop. We're going to kind of go over it on Thursday anyway. So kinetic energy is 1/2 mv squared. So this is when I bring up the example of dodgeball. So dodgeball, if you want to have more energy, you could either throw something heavier or more mass, is the correct way of saying it, or throw something faster. So if we go back to our thing dropping, I could increase the amount of energy or my ball has, but instead of dropping it, I could throw it down. So even though my height isn't that high, if I increase the velocity, I'm going to increase the energy. So that's pretty cool right there. So you have energy that's related to mass and velocity. So looking at the units here, same thing. You have mass, velocity, velocity. I could have it like this, but if I rearrange it, move one of the seconds to the middle term, then what I could do is kind of manipulate it. So here's mass acceleration, which is newtons. So even though it doesn't seem like potential, the units are the exactly same, Newton meters or joules. So both potential energy and kinetic energy are both measured in joules or force times a distance. The last thing that you have in 8th grade is that you have mechanical energy, which is what we're going to mostly use. There are other forms of energy, and in class we'll kind of explore them, but it's kind of hard to kind of show it. So I have something called happy balls and sad balls. They're bouncy balls, and some of them work better than others, and it has to do with this part. So these are, even though we have ways to get some of this energy back, we do have devices that could change heat into energy. We have devices that could change light into energy, solar panels. But in most cases, eventually these three things are going to lead up to energy loss to the system or to the environment. So if you think about it, when you're using a motor or battery or even your phone, it creates heat. And once that heat is created, we can't utilize that. So that's what makes our phones or cars not 100% efficient, because in our combustion engine, a lot of that energy is lost in heat. I have objects in my class that shows how objects, when they collide, they create light and heat. And that's also stuff that you can't capture. So even though we have solar panels, if you burn something, it's really hard to recapture the energy from the fire part of the burning. So that's also lost in sound. Once you create sound, it kind of gets lost into heat as well. So these are things that do exist, but they're not useful energy in the sense that we can't harness it. The useful energies that we have is potential and kinetic. So most cases for us, potential is some sort of battery or a hydroelectric dam or something like that that's storing it up, chemical reaction. And then we're going to use the kinetic from that potential energy to create most likely electricity. So that for us, most of our energy comes from these two relationships. You have stored energy as in fuel, a dam, nuclear energy, and then when you're burning that fuel or letting the water run down the dam or the wind blow the turbines or the solar panel, then you have kinetic. Let me check. A steam turbine, it does use heat, but once that heat is used, then what happens is, so you're heating up water to change into steam, but a lot of that energy, even though combustion works the same way, you're heating up, you're making you're changing from liquid to gas, but a lot of that side heat can't be harnessed. So even a steam engine, even though you're using heat, we're not using all the heat. A lot of it is also lost into space. So when you're boiling water, yeah, a lot of the energy is going into the water itself, but a lot of it is also dissipating into the environment. So that energy, where it dissipates in the environment, you can't harness. That's what I was trying to say. So we can harness some of it, but not all of it. So the ones that dissipate into the environment, it's gone energy. Same thing when you rub your hands, the friction is heat that you can't reharness again. Okay, but it's useful because if your hands are cold, you can use it that way. All right, so technically total energy is potential, kinetic, and internal. So this is always conserved no matter what. So your total energy is always conserved. Now for us, mechanical energy is potential and kinetic. So it depends on the problem itself. Sometimes we're going to say all mechanical energy is conserved because for us, physics is much easier to solve without friction. But in reality, in real life, mechanical energy is not conserved because we have internal. So it is conserved, but total energy is not conserved as in physics world because we can only measure mechanical and we're not measuring the internal itself. So so let's say the best example is a bouncy ball. You drop it, it has potential, it has kinetic, but it doesn't bounce back to its original position because of the energy lost in internal. So we only see mechanical, and for us, when you drop something like a bouncy ball, mechanical energy in our eyes aren't conserved because a lot of it is lost in internal. So it's kind of a weird balance between the two. As we do more problems, it'll make more sense what I mean by that. But we're going to assume for our problems, everything is conserved, both total and mechanical, because we're going to imagine that there's no friction. Bye, Evan.
Yeah.
Okay.
Bye-bye.
Back to this original one, and then we can look at our polls. Hopefully everybody was able to vote. So most of us say the yellow one's going to be the fastest down, and most of us said the red one is going to be the quickest down. So we can actually solve for this if we simplify the problem. So what I did is I just made it into 3. There's no reason to do 4. I made one that's very steep, one that is semi-steep, and one that is the least steep. So we have a 60, 45, and 30 degree angle. And to make life easier, I made them straight. So we're going to solve for each one of these. I'll do the first one with you, and then I'm going to ask you to do the next 2 on your own. And then hopefully with mathematics, we could go back to our poll and answer those questions that I posed in the very beginning. Since we're not able to kind of physically do it in front of you, that slide is at work. So let me pull out my pen and just kind of just show you. So we're going to solve this by using the tools that we found from our last 2 units. So I'm going to break this down. I'm going to just focus on the 45 degree. So here's a right triangle. Here's, let's say, the object that's going down. I have a mass of 50, but you'll notice really quickly that you don't really even need the mass. And then you have forces of gravity acting on it. We're going to ignore friction. So in this case, you only have 2 forces acting on it. You have force of gravity, and then you have force normal. Our goal is to answer these questions all the way back to our second unit. We want to have values to answer this because our goal is to find how long it will take, which is this one, time, and how fast at the bottom, which is velocity. So those are the 2 entities I want to solve. I know for this ride, I start off with initial velocity of 0, but I don't know what the acceleration is and I don't know what the distance is, but we could figure it out based on what I gave you, which are angles and height. So by looking at it, we could first find acceleration by doing this. Gravity's down, but we are only concerned about this one at this direction, which if you break down gravity, here's FGY and here's FGX, is this one, FGX. That's the only one we're concerned about. So we're going to do, this is going to be my point of view. This will be my Y. This will be my X. So sum of all forces in my shifted X is just going to be FGX, which is equal to MA. And that's the thing I want. I want that A. FGX, if you remember back, sine of theta is opposite over hypotenuse. So in this case, here's 45. Opposite is FGX. Hypotenuse will be FG. So FG sine theta is equal to FGX. So this should be from 2 units ago. No, 2 units ago. No, last unit. So FG sine theta is equal to MA. I'm going to change this to MG. Okay, so you'll notice that the m's cancel out. So it doesn't even matter if the rider was 50 kilograms, 100 kilograms. It's just going to cancel out. So there's my A. A is equal to G sine theta. So I'm going to plug that right here. G is 9.8 sine of theta. Okay, to find this distance right here, we could use angles as well. I gave you 10. Now, in reality, that object that I have is not 10 meters tall. I just want to make units that are nice. So I picked 10 and I decided to pick 10 just for the sake of doing meters and not converting from centimeters and stuff. So you have that, and then you have an angle. So here you have 45 opposite over hypotenuse. So you could do the same thing with displacement. So if this was 10, this was 45, we could figure out this distance right there by our angles. So sine of theta, remember, is opposite over hypotenuse. So in this case, it is 10 over x. So x sine theta equals 10, or if we're looking for x, 10 divided by sine theta will give us x, which is d. Okay, so those are our two unknowns using the stuff that we learned before to solve for it. Okay, now knowing that, I'm just going to plug it in. So for my case, I'm solving for 45, so I'm going to plug that into there. So sine 45 times 9.8, let me look for my answer, is 6.93. And then this one is 14.14. So if you plug it in, if you're in degree, those are the two answers that you have. Sine-wise, you could think of it both ways. You could think of them as both down, so you could have them both negative, or you could think of them as both to the right, both positive. Whichever one you choose, it doesn't matter. As long as they're the same, you're going to be okay. So now we have 1, 2, 3 things, and we can solve for both VF and T. So I'm going to do that. So these are the two equations you're going to use. VF squared equals VI squared plus 2AD. I don't expect you to memorize this. This would have been on your cheat sheet. And then for this one, it would be VF equals VI plus AT. This one will be easier to do first. For both of these, VI is 0, so you don't have it. So it's just 2 times 6.93 times 0.14. And then if you take the square root of that, you should get 14. Plus or minus, technically. And then you can use the answer over here to solve for t. And t, you get about 2 seconds, I believe. That's a really ugly t. Let me fix that. So what I like you guys to do is to do the same thing, but solve for both 30 and 60. Now, you don't have to do any of this work up here, because all you have to do is just plug in the new angles. So for 30, just plug in 30 here and 30 here. You'll have 2 new accelerations and displacements. Plug it into these 2 formulas right here and solve for VF and T. So do that for both 30 and 60, please. And then look at your answer for the pole and see if your guess was correct. All right, I don't see any questions, so I'm assuming everybody kind of had enough time to kind of digest. Hopefully everybody was able to see that even no matter what the angle is, your velocity should be the same, right? For 60, you get 14 point. They all get about 14. So I think this one's a little bit higher based on rounding. This one's a little bit lower based on rounding, but you get about 14. The times, though, aren't the same. I believe this one's about 2.8. This was 2. And this one was, let me check, I think 1 point. Where's my answer? 2.8 and 1.6. So this one's the fastest because it's the steepest. This one's kind of in the middle. This one's the slowest because it's not as steep. But at the end, they're all the same. So let's look back to our poll. And I think most of us were kind of all, I wouldn't say right. Let's see, which one would have been the fastest? Let's go back to that original picture. Too many windows up. So based on what we found, the fastest one should have been blue. So 6 of you voted that one. And then the one at the fastest at the bottom is kind of a trick question. And only most of us picked red, which makes more sense. In real life, it would be red because of friction. But in our non-friction world, even in classroom, it's pretty much the same. There's not enough friction here to make a difference. But they should all be the same at the very end. But you're right. If there was friction, red will be the one that makes the most sense to be the fastest at the end. So if you're picking a ride at an amusement park, the slides, I'll pick red to be the fastest on the way down. All right. So let's kind of prove that another way. So when you look back at this, why is it that all the velocities are at the same at the end when they're experiencing different accelerations, right? The steeper one's getting the biggest G, or biggest gravity, experiencing the most gravity, and the one that's like yellow is experiencing the least amount of gravity, but yet they're the same at the end. So why is that? Anybody want to contribute in the chat? Why do you think? Same potential. Okay, what do you mean by same potential? What's the same? I'm looking for an even simpler answer. You're right, though. It is potential. If you go back to potential, same heights. Awesome. So that's the thing. So when we're looking at potential energy, we'll go back to that slide. Where is it? Oh, I went too far. It's this one right here. So if you look at this slide, MGH is what we're concerned about here. So the potential for all 3 of, or all 4 of them are the same. They all start at the same place. Where is that slide? They all start at the same place and they all end at the same place. So the potential energy at top is going to be the same for all 3. So they all have the same. Oh. They all have the same potential energy at top, and technically they all have the same potential energy at the bottom. I think the better way of saying it is they have the same total energy at top, technically mechanical because we want to ignore friction, and same total energy down here, but we're going to ignore friction, so we're going to call it mechanical. So let's actually try to solve that, and you're going to see it's much, much easier. So at the top, you want to find the mechanical energy at the top. And for us, mechanical energy is conserved. In real life, it's not, but we're going to say it is. Oh, I could write an M just for the sake of physics. So the bottom. So the mechanical energy at the top is going to be the same as mechanical energy at the bottom because we're ignoring friction. So here we have potential and kinetic. And here we have potential and kinetic. Here the potential is mgh. And I'm just going to leave g or m as m because I want to show you that mass doesn't matter as well. I believe we used 9.8. Height was 10. And then here, height was 0 at the bottom. So here it's 0. So here we have a total. Here kinetic energy was 0 because it starts from rest. Here we have a total of 98 M. So 9.8 times 10 is 98 m amount of energy. So that means over here, we also have 98 m energy. So if potential energy is 0, that means kinetic is 98 m. And I probably should plug it in just to make life a little bit easier. If you plug in m, that's 50 times 98. So, or 49,000 or 4,900 joules, 4,900 joules, 4,900 joules. Now, kinetic energy, remember, is equal to 1/2 mv squared. So that's why when I left the m there, you could just show that the m cancels out. So you just have 98 equals 1/2 velocity squared. And you solve for it, guess what answer you get? 14. So you could do this much quicker and easier. Don't have to worry about angles. And the reason is because all that matters here is the starting point and the ending point. We don't care about what happens in between. It could go like this all around. As long as there's no friction, your starting point and your end point is all that matters. Now this one technically won't work because it's higher. So I probably should do a better drawing. There you go. Okay, so it doesn't matter what happens in between. As long as your starting point and end point is the same, it's going to give you the same answer. Any questions on that? So that's our last tool of the semester, which is energy. And this one, the middle part, doesn't matter. All we care about is the beginning and the end. So back to 8th grade, those kind of problems. I posted up a good practice problem that does include friction and no friction of the same thing. And on the second problem, it is the deriving thing. So that's kind of the homework. I'll have the answers posted by support block, and then I'll have this lecture posted as well. Are there any questions?